Okay, so orientation, right? So in general, a lot of what we see in terms of people using parametric design tools is in regards to addressing complexity, right? So when I talk about complexity, I'm talking about, large data sets, huge amount of variation, right? So very little standardization or modularization, right? Everything is kind of transforming and changing and happening in a very smooth and organic way, right? And, the reason that we see that a lot is simply because, well, that's what the tool offers, right? That's the benefit of working in parametric design, right? And so I think a lot of people who specialize, right, kind of focus on that aspect of it. Of course, that's not the only way, you can use it, but, some would argue that, well, if you're not using it in that way, then, you're not really using the tool for what it's good for. So, why don't you just, do it some other way? We're not here to take sides in that argument, but I would like to demonstrate in a way why some of the strengths of that tool and this method of working, right, is that it really opens a lot of doors. Things that were, you might have thought took too much time or too complicated or whatever aren't, necessarily, that's not necessarily the case when you're working in parametric design tools. So it opens doors basically. So today we'll be looking at a few things, and we'll start with this idea of orienting, right? And so when we talk about orienting, we're really just talking about kind of copying, pasting geometry, right? But copying and pasting geometry with control of the positioning, right? So, I think one of the things about digital design practice from the very beginning, right, was that everybody thought, wow, that's going to be so useful in our practice, right? Because now we can make a block in AutoCAD, and we can, whenever we need a bathroom, we can just copy and paste that from one place to another. We don't have to, draw it over and over and over and over 1,000 bathrooms, right? And that was like a huge thing, early days of digital design, right? And I think parametric design had kind of the same development early on, which is like, oh, well, look, we can deal with lots of geometry, lots of variation, and we can copy geometry, and every geometry is going in a different direction, and that direction is controlled by whatever parameter, right? And so that became kind of an obsession with parametric design early on. So we're going to look at some examples of that, right? So orienting geometry was one of those things. Now today, for our examples, you may notice that some of the methods that I'm going to use today are a little bit, let's say, unnecessary. For instance, I might draw a line in a very strange way that takes lots and lots of steps that are extra steps or extra tools that you don't necessarily need to use to draw that line. Just know that I'm doing that today because we're at a point in, I think, the development where I'm going to try to introduce to you some more components, right? And use them in the definitions, not necessarily because they need to be there, or that's the only way, or that's the easiest, or that's the only way to do it. It's because I want to show you guys or expose you guys to some more options, right? So just be aware of that, so you're not annoyed at the fact that we're taking 10 steps to draw a line. Okay. So that said, let's draw a line. So to start with, we want to create a system, right, where we're going to orient geometry according to the shape or the curvature of a line, right? So if we go into our curve tab, you can see we'll pick a line type, and we're going to use the SDL line, right? I think we looked at this before, right? It's just a line that requires a start point, a direction vector, as well as a length definition, right? So let's get those all in there first. So vector, let's define a plane, right? So we can use, for instance, the XY plane, the default plane as an origin, as our starting point. We can use a vector, unit vector. Let's say we want to go in the X direction for this line. And you can see now that we've defined a direction, it's already drawn that line because the length by default is 1. And let's use another slider here to draw the length, right? So there we are. Okay, so we have our line. Now we want that line to, say, move in various ways, right? Not because right now the line tool, all it does is draw this kind of straight line. But let's say we want to rebuild that so that we can, have some control points and maybe make a wavy line or a curvy line or something like that, right? So what can we do? Well, we can take this and we can extract, right, some data from it, right? So for instance, now we kind of talked about that already. So if we want to extract something from it, we probably will look at the type first, which is the line. And then here we're looking to use the analysis tab, right? And we say point on curve, right? So you can see here that this component says evaluates a curve at a specific location. What does that mean? Well, point on curve, right? So you get a slider, right? And when you connect your curve to it, it creates a point. You can see it here moving in space, right? Somewhere along that curve, right? And if you notice, the values here aren't really important, right? The line is, 28 units long. And if you slide it to 0, it's kind of goes to 0. And at 1, it will go to the full extent of the line, right? So if we go to 0.5, for instance, right, we can be pretty confident that that's the middle of that line, right? And you can see here that now, I can use this component to find, or generate several points along that curve, right? So 1, 2, 3, 4 points along that curve. Okay, so that's very useful. Now, if we start to move, right, some of those points around, right? So we're going to use our move component, transform, move under the Euclidean category, right? We can say, okay, 4 points, we want to be able to move them around in space. So I'm going to input all 4, and remember, order of these connections, right, matter because they change the order of those items within the list structure, right? So if I had connected any of these, right, in a different order, they would appear different in our our data list, right? Now, right now, all the motion is the same, right? So if we look at this now from our perspective view, you can see that those 4 points, right, got moved up 10 in the Z direction, right? Now, what we want to do is that we want to be able to, say, manually control, right, that translation, right? And, in this case, let's say we're fine. We'll let it move in the Z direction. That's the direction we want. So we'll use a unit vector Z, right, to define the direction. But we also need to input a factor, right? So again, we could connect a whole bunch of sliders to that, or we could, do whatever other options that we have. But let's try to use a different tool. Let's say we want to create a gene pool, right? So in this case, we can use the gene pool component, right, as a collection of values, right, that we want to use, right? So again, this is very handy if you want to be able to adjust these and move them around later on, right? Now, by default, the gene pool you can see here comes, right, with 1, 2, 3, 4, 5, right? And we're really, we only have 4 data points here, so we can come in here, edit our gene pool, check the values to see if, we're okay, right? Oh, actually, there's more here. And we only need to have 4 values, and I'll accept the rest, right? So now we can individually control the position of each of those points in space, right? And that's something that's handy because we can come and do that whenever we want in our design, right? We don't have to define everything right away if we're not clear. So from there, now that we have those points in space, right, we can go ahead and try to draw our curve, right? So let's go to our curve components, and right, if we want to draw a kind of free-form curve, we have a few options here. I think we used NURBS curves before, we used polyline before. There's also one which is interpolate, which is commonly used as well. Very similar to the NURBS, only that with the NURBS, you don't pass through those points, right? You kind of draw like a mean average. Whereas with the interpolate, what it does is that it guarantees that the curve that you draw will pass through each of those defined points in space, right? So again, useful to know depending on what you're trying to accomplish. Now, these aren't, these all have default values, so there's not anything specific like this is open or closed, or that's whatever degree type of curve that you're using, right? Those are all things that you can play around with and change on your own. They don't impact us here in this example, so we'll just leave them at their default setting, right? Okay, so what if now we're going to say, okay, we want to orient geometry along this curve, right? So the first thing that we need to consider is what's the geometry that we're going to be working with. So if we're going to be working with geometry, that means probably we will go under our surface tab and look to create something, right? And this can be any geometry type, no matter how complex or how simple, right? We're going to use a primitive geometry for this example. Let's just say we use a cone, but of course, you could use any number of things, including, you could be copying and orienting whole buildings if you want, but we'll just stick to a primitive geometry for our example here. So here you can see that as I brought in the cone, right, a cone appeared at the origin, and we maybe want to define, its characteristics. So let's use a couple sliders for the radius as well as the length. Okay, so let's say that's our cone, right? And we want to copy or iterate this cone all over this curve, right? So what can we do? We can go to our transform tab, right? And then we can find our orient component here. So you can see the orient will take a geometry, it'll take a source plane as well as a target plane, right? So what are those? Well, so the geometry, what we're interested in orienting is this one, the cone, right? So there's no real question about that. And then the target is a plane, right? And of course, right now we haven't defined anything, so we're just creating something here. But what we want to do is say, okay, let's see if we can find points on this curve which we want to copy this object onto, right? So to do that, we go to curve and we say utility. There's a division tab, so we go to divide and we say, okay, curve, divide by what count. We want that to be something that we can modify. So let's give it a slider. So there's 10. It's divided into 10. And we say, okay, so those are our targets, right? And you can see right away, with the source being the default X and Y plane. So if I made this explicit for you guys so you can see very clearly, right? The source is the XY plane, right? The geometry is this cone, right? And the targets are these points here on that curve, right? So what it does is that it then orients, right, this geometry onto those points along that curve, right? Now, if we come in here and we start to change the characteristics of that curve, right, you can see that it doesn't disrupt the basic logic, right, of our orientation, right? Now, what if, right, you can see right now that, we have defined a target, and we've defined the target using a point, right? But in fact, the target can be defined as a plane rather than just a point. Because we're using a point now to define that location, right? It maintains the default orientation, right? So it's always going to be, kind of pointing up vertically, right? Now, that's not very interesting. What if we wanted, for instance, this cone to follow along the curve, right? So that it actually goes from pointing up, right, turning over, and then starting to point down, for instance, right? What that means is that we need to be more specific about how we do the targeting, right? And so we need to define a plane rather than just a point to use as our target. So if we go under our planes, under the vector tab, you can see that we have a lot of different kind of ways to define a plane, right? So far in this course up till now, we've probably just been looking at these kind of coordinate planes like the XY, the YZ, and the XZ, right? But we haven't really looked at some of the more complicated ways to define planes that aren't, that aren't along any axis, basically, right? So one way, and for us, right, in this case, if we look at this component here called plane normal, right, you can see it says create a plane perpendicular to a vector, right? So what does that mean? That means I'm going to generate a plane, right, that is in the same direction, right, as the vector at that point, right? So if you imagine this curve here, right, and at this point here in space, what's the direction of that curve going, right? That would be a way for us to define, right, the direction of our plane, right? So if we wanted to, what we would need to do is we would need to find the direction of the line at that point in space, right? Now, you could do that using some of the curve analysis tools, right, to find the directionality. For instance, here, evaluate curve, right? But fortunately for us, this one, divide, the divide curves already has tangents built into it, right? So we can just rely on the default tangent, right? And use that to define our direction, right? Our points then are the origins, right? And so you can see that these planes now are generated at each point, right? And the direction into which those planes are oriented, right, are in relation to the normal tangent direction. So in relation to the tangent direction of the point on the curve, right? So if we now use this plane, right, as our target, you can see now that the result, right, is that these are now oriented and they're following along, right, that curve. Now, in this example, we have here, when we generated the cone, it's referencing the base as the world XY here, right? And so when we look at this now here on this curve, we'll see that, yeah, so it does pass through kind of the center of the bottom circle at each of these points. However, at the tip, you can see that there is quite a big misalignment then, right? Because, just because of the shape of the geometry and how tall it is, right? So, maybe a way to deal with that is to define the source, right, a little differently. So let's say we move our source up slightly. Transform, move, geometry, motion, vector, z direction. And then we use this plane here. So you can see that if I were to define, right, the source plane, right, at the tip of that cone, then now when we look at the positioning of this object in space along that curve, right, we can see that now the tips will always be, aligned right on that curve, right? Although, you have the opposite problem where, now when the line exits, right, the back of the geometry, it's not right, right in the, in the center, right? Now, for me, I think you could obviously, you can do a compromise and you can say, oh, well, let's just pick something, kind of in the middle, right? And that will be kind of average everything out. That's fine too. But I think for me, I would like that the point is always on target and then the rest of it can go kind of the way it goes, right? So now that all of that is set up, you can see how easy and flexible it is, right? Because now, we can again go back and change all of these factors inside our definition from the previous sections, whether we're talking about the shape of the original geometry, right, the number, or the size, fewer, more, the shape of the curve, right? We can be pretty much guaranteed that no matter how we define these things, right, our geometry will still respond appropriately, right? So this allows us to create design definitions in a very flexible way that leaves lots of kind of room for adjustments and tweaks, right, to your final design, right? And you can see how, it creates the opportunity for a lot of variation, right? That, is kind of, we say is a kind of parametric characteristic. But at the same time, when we're talking about architectural building and manufacturing, right, it adds a level of complication, right, that maybe not everyone is thrilled about, right? But hopefully, with better fabrication tools like, 3D printing, laser cutting, CNC, and whatnot, those kind of limitations can be addressed because those tools in general don't care about, it's not like mold making or casting or, all these other types of manufacturing, which rely on the standardization of components and parts, right? They're much more independent, right? And able to address mass customization and variation, right? So, that's our first kind of example of working with orienting geometry. Now, why don't you guys try that out and we'll come back and we'll look at another example. This that's, a bit more complicated because we'll be dealing with surfaces instead of just looking at curve geometry. Okay. Okay, so in the next example, really we'll be building on what we've already done, except instead of just working with a line, we're going to go ahead and transition that into a surface geometry, right? And you'll see this a lot in kind of facade design, but let's just look and see what happens if we copy and paste. So I'm going to go ahead and generate from this same method of line creation a surface, right? A modifiable surface, basically. So here, if we turn a preview on, you can see we have that one curve like we had before, right? And except that now we have actually 3 of them, and we're gonna modify it a little bit so that they are useful in, say, generating a surface, right? Now, the only thing right now that I think is a little bit disappointing in terms of what we're working with is that they're kind of still planar in this direction. So I kind of want to add something in terms of their motion to offset it a little bit, right? So, you know, you could do that kind of in a lot of different places, right? But one easy way is to just change where we start the drawing from, right? So right now we define the starting point with this origin, right? And if we move, transform, and define, we're going to use a vector to move it in, let's say, the y direction, right? By a certain amount. Let's say we use a slider with the 100 here. You can see now we have a more three-dimensional set of curves for us to use to generate our starting surface, right? Kind of want to change this. Let's maybe invert this, right? Get something more interesting. Okay, so then we have our 3 curves, and let's use our surface components, freeform, loft. And we're going to use the loft basically to take those curves and make it into a modifiable surface geometry, right? So right now, by default, we have kind of this situation. I think maybe these are too far apart for what we're doing. And maybe we don't necessarily need to start so exaggerated with how these values are. Okay, so let's say we start with this shape. Okay, something easier to visualize for now. We can change that later on in the process. Okay. Okay, so there's our surface, right? So if we wanted to, say, use that orient component again from our transformation tab, but not be restricted to a surface, what would we need to do? Well, if you remember a curve, what would we need to do? If you remember when we were working with the curve, the first thing that we needed to do was we need to generate a series of points, right? To locate where that geometry gets distributed, basically, right? So similarly, what we need to do with this surface is find points on that surface, right? So if we go to our surface tools, right, you'll see under utility, there's one called divide surface, right? And that's very handy because what that does is that it lets us populate our surface with a lot of points along the UV coordinates, right, of that surface. And we can define the UV manually if we want. So we'll use sliders to do that. And it, by default, right, this divide surface provides us with points in space, these points, as well as their normal direction, right? Which is very useful to us because if you remember here on the divide for the curves, it provided us with tangents, right? Which allowed us to then generate a plane to orient that geometry, right? So this is a similar idea, right? We have points, right, that serve as our kind of location, right? And normal to give us the direction. Now we need a component, again, that will basically allow us, right, to point our geometry. So we go back to our vector normal. We say origin z-axis, right? You can see how when you connect the normal to the z-axis, the planes are kind of hugging the surface now, right? And use that again as our target. And we have, of course, our source and our geometry, right? So the geometry, let's say we use the same cone as we did before. So I'm just going to copy that over. Use a cone. And by default, it's using the, the world XY as a starting point, right? So now if we look at this, you can see that this geometry is being oriented onto that surface, and it's preserving the directionality of that surface as well, right? So you can imagine here that, it's almost like hairs growing out of skin, right? So from here, if we say bake, I'm just doing this because I want to see what that actually looks like instead of just relying on the preview. Yeah. So you can see that it's an easy way to get geometry to roughly follow the shape of a surface, right? And it's very useful in situations where you're working with things like facade panels or geometric skins and stuff like that, right? So really, that's just a slightly more advanced version of the previous example, but I wanted to make sure you guys understood that, this component orient doesn't have, as a source and a target, it doesn't have any kind of geometrical limitations, right? All it requires is a location, right, and a direction, right? And the whole point of being able to do that is that we can generate very complicated facades using simple surfaces, right? So in that afterwards, right, if we need to tweak and modify that surface still, you can see how easy it is to continue to address that, by modifying our original surfaces, right? So that's a very good way to develop kind of facade patterns and skins, because you don't waste a lot of energy, right, trying to draw things and then figuring out they don't work and then needing to modify it and then having to redraw, all those kind of details all over again, right? So it's a very kind of practical way to do something very impractical, if that makes sense. Okay. So next we will go and look at an example where it's not just orienting geometry, but it's actually transforming the geometry and morphing the geometric characteristics of the geometry. So one thing to be aware of is that, and we'll look at this again when we get there, I guess, is that all of the geometry that we're looking at now, right, has maintained, right, a certain dimension, right? And when we talk about morphing, right, it's a similar idea, except the base geometry will transform with the surface that you're working with. Okay, so why don't you guys try this first, and then we will look at morphing afterwards. Okay, so now in our morphing example, where the geometry itself is transforming in relation to the surface that it's being placed onto, I'm going to copy and paste from our previous example this same surface, just so we don't have to do that all again. Okay. What that means is that the reference geometry, and before we'd always use kind of planes as our reference geometry, right? And that was because essentially all it needed to be able to define was, a plane and a normal direction, right? A tangent or a vector or something like that. Now with the transform and morph, right? Because the geometry itself needs to change shape, then what that means is that we can no longer rely on a plane only to define the characteristics of this shape, right? So instead, the way that we usually approach it, if we look at the morph component, is that you'll see there's something called box morph, right? And with the box morph component, we also will need to use a surface box, right? So here, effectively, what we're doing is we're creating a three-dimensional surface, right? So, I mean, a surface with some thickness to it to define the thickness of that geometry, right? So what we do is we say, okay, well, let's create surface boxes, right, that are twisted in relation to the UV coordinates, right, that we have set up here, right? So if we say, okay, that's our surface, then we want to, again, kind of divide our surface up into parts, right? before even generating this box, right? So to do that, we have under our Surface tab, Utility, a ISO trim. Right. Last time we had used the divide surface, and the reason that that worked for us is because we're looking to find a point or a position on that surface, right? But in this case here, for the twisted box, we need to provide it an actual surface to generate that box from, right? So instead of dividing it, what we're going to do is we're going to use the ISO trim, right, to take our surface and divide it up into sections or smaller surfaces, essentially, that we're going to feed into our twisted box, right? So you can see here that the ISO trim requires a domain, right, which essentially is something that will help it to define how many cuts, how many segments to cut that surface into, right? So we know our domain tools are under the Math tab. And if we look, there's one called Divide Domain, which is made for surface geometries, right? Before we had looked at kind of some of these earlier, when we were talking about remapping and defining a range, right? This is, based on numbers only, right? Now we have things that are more related to actually working with geometry, right? And so this Divide Domain allows us to divide surface geometry. So we'll use the surface itself as an input, right? And then we'll use a UV count to determine how many segments we're going to divide that surface into. And then we'll use that as our domain, right? So you can see here that now, instead of being one surface, right, defined by 3 curves, what we have are, 100 surfaces, right, that have been cut from that original loft, right? And of course, the number is dependent on what you set the UV count here to. So from there, you can see that the twisted box, right, actually requires, the same thing, basically a domain and a surface. So we're going to go ahead and use our domain as described here, right, to generate this twisted box. And you can see that it's kind of creating this thickness, right? And that can be, you can control that using the height. Here. Okay, so I want to do something first. Didn't work. I guess I will just make this a negative value to get the direction that I want in terms of the offset of the box, right? Okay, so it's generated those twisted boxes for us, right? And those are our target, right? We want our object to fit into those boxes, right? Now, what is our reference though? Well, our reference is not going to be this cone. A reference needs to be a box as well, right? You can see here it says reference box, right? So the easiest way to create a reference box is simply to go to our surface tools, right? Go under primitive and choose a bounding box, right? So we've worked with other boxes before, right? Box rectangle, 2-point box, center box, right? Bounding box simply takes the contents of whatever it is you have, right? You throw it in there and it will create a box around it, right? the minimum box size required to fit that object, basically, right? So from there, we use that box as our reference. And the geometry, right, is our original cone, right? And you can see that once we've done that, we hide maybe some of the unnecessary stuff. Maybe that's useful to see. You can see that the geometry is in a way similar to what we did when we were orienting the geometry, right? It moved it onto that surface. However, if you pay attention to it, you'll notice that in this example, right, all of these geometries are kind of scaled to fit, right? So they're not really cones anymore. Some of them are squashed a little bit in this direction or in that direction, right? Depending on, how it got divided, right? And so I think it's safe to guess that not a single one of these cones, right, are identical. So remember in the previous example, I had mentioned that using the orient component was a kind of very practical way to do something impractical, right? Because, you were using a kind of standardized component and you were putting it onto a organic curved surface, right? But then, the fit doesn't always seem that uniform, right? You may have some gaps in between and stuff like that. Whereas the morph component, what it does is that it really transforms your module, right? And forces that module to fit onto that surface, right? So this would be a, impractical solution, right, to an impractical problem, right? But again, in a way, this is the more ideal solution, right? Because this is pure to the original concept, right? And many people will prefer the aesthetic of this to the previous example, where every module was identical, but you had some kind of gaps in the seams were kind of showing depending on the geometry and the shape that you had set in your surface geometry, right? So it's really a personal choice, I think, at this point. Which aesthetic you prescribe to. You should know that. What you need to keep in mind, I guess, in when you're making that decision is what are the kind of fabrication tools that you have available, right? If you're working with a lot of CNC and 3D printing and stuff like that, then this solution makes a lot of sense. Again, because those types of fabrication methods aren't particularly concerned with modules and standardization, right? Whereas if you're relying on things that are built on site that need to be defined dimensionally using drawings, right? And it's not directly, sending data from a computer to a machine. That's, your mode of fabrication. Then, you really, you couldn't really imagine trying to describe these geometries, right, to a builder, right? That simply couldn't be done. You could spend, 500 drawings and you wouldn't be able to describe, the whole thing, right? And not to the extent that would be needed for a builder to build it, using traditional means on site, right? So, parametric tools and digital tools allow us to a lot more design freedom, but at the same time, it's really important to understand your fabrication tools, right? What you have available to you, in order to make good design decisions about which method or what your kind of design position is when you're setting up your projects, right? So it's just something I think to keep in mind. All right, so morphing, right? Again, very similar to what we were looking at before, right? Only now all the geometry, something else to keep in mind. So before, when we had this cone in the orient component, right, you would have noticed that here, if we adjusted the size and shape of the cone, it had a pretty dramatic change on the outcome of that geometry, right? Whereas here, now, if we change the size of this cone, whether it's the radius or the length or whatever, right, it has no impact really on the final outcome in geometry, right? Because this box that we're using as a reference, right, is transforming with these changes that you made, right? So it's the relationship really between this box and your twisted box, right, that controls the geometry, not the actual geometry itself, right? So the definition or the construction and shape of this cone excuse me, isn't going to have any real impact on the final outcome once it's morphed onto that surface, right? Where it will have impact is, if you change, for instance, the height, right? Because that's changing the shape of the box itself, right? That it's being morphed into, right? But that said, you can imagine then that there's not too much, in this respect, there's not too much that you can do in terms of transforming the geometry once it's in these two boxes, right? Whereas here, the cone, as it's being oriented, you can make lots of dramatic changes to this geometry, right? And as it gets oriented on that surface, those changes and those modifications will be maintained, right? So depending on the circumstances, on what you need for your design, that's something to keep in mind as well. Okay, so try that, and we'll wrap up this week's session with a little bit of a play in our mesh tab, specifically using some of these Voronoi stuff, because everybody loves Voronois. Okay. Okay, so let's look at our, I guess, last exercise for the day. And we're going to look at something that I guess most of you should have already seen. I don't know. I feel like it's probably one of the most overused components. And it's something that I think people gravitate to because it seems easy to generate, a pretty strong visual effect. But at the same time, I would warn you that, because it is so overused, it's quite boring for, I guess, most people today to see this strategy being used. But many of you will recognize the Voronoi diagram probably from the water cube. From the Beijing Olympic. Right, you probably have all seen images of the Beijing Olympic water cube, right? And so we'll talk a little bit about how to generate that kind of effect now. So this is kind of the first time that we're moving into our mesh tab here in Grasshopper. And so just like all the other tabs, you have your analysis on the left and your utilities, right? And then you have, a kind of few basic things, right? Like generating primitives, mesh shapes, as well as some kind of pre-programmed mesh, I would call them effects, right? So we're going to look at the Voronoi today, which you can see here. And what that does is that the Voronoi diagram is something that was developed to simulate soap bubble effects. So if we do a quick search, you can see that essentially what this diagram does is that it divides, it's a way to kind of divide space, right? look at some images. And with the thought that, you know, every space kind of has a center point, right? And now you're going to tell me, well, those points are nowhere near the center of those cells, right? You know, some of these are way off to the side, and some of them, you know, are tucked in at a corner somewhere, right? If we were looking at a center, it would be here, right? Well, so the way that this diagram is generated is it takes for, you know, it takes as its kind of base condition, right, a field of points, right? And those, you know, may be important locations, right, in your plan or in your city or whatever, right? And then the diagram says, well, how do you, you know, divide up the space equally or evenly or fairly, right, for all of these points, right? And, you know, it's quite strange because you think about fair and equal and you think that, oh, well, everybody, you know, or every point should have the same amount of square foot, or every point should have the same amount of overall space, right? But actually that's not the case, because of, you know, those points, they don't move, right? And so the logic behind it is more like, well, I'm going to take the distance between each of those points, right? Find the midpoint and make a line, right, that is perpendicular, right, to the line that you draw between them, right? So that's, you're dividing the distance between here and here directly in half. And then you continue to do that, you know, with all of the relationships between each of those points, right? And you see that this diagram kind of emerges on its own, right? And you can say, well, given, you know, the location of those points where they were in space, right? If I were to, you know, kind of equally divide up the space so that they're, you know, you're sharing with all of your nearest neighbors, right, evenly, that's, you know, the shape that you arrive at for the division of space, right? Or the even or fair division of space. And so with this diagram, then that means, okay, so it takes points, right, as its input. So we need to generate a field of points in order to work with it. And so what we're going to do is we're going to go to our vector tab, right? Because in our vector tab, you see we have, you know, a lot of different ways to construct points, right? But I don't want to just, you know, construct points one at a time. You know, I want to be able to construct a group of points all at once. And so to do that, you know, there are a number of ways to do that. You could, you know, use a grid and then do a random reduction of that grid to after you find all the kind of discontinuities on the edges, right? Or you can also use what's provided here, which is a populate 2D or populate 3D, right? We'll start with just using a 2D for now. And what that does is that it automatically kind of generates a region, right, that and populates it with points in space, right? So you have some control over, you know, the shape of that region, right? You can define it with width and a height, and you can change the count number, right? So by default it's 100. Let's say we want some flexibility with that, so let's go ahead and say we want a slider to control the count. And again, whenever you see seed, that just means to do a recalculation, right? So you didn't change any of the parameters, you're just wanting it to recalculate and give you another option of the same, you know, the same solution basically. And so within this, of course, you can also add additional points if you want, just in case you have some specific locations that you think are particularly important for your design, right? So for now, we'll just accept the default region. We're not going to worry about changing its shape. Although actually, because we need to define a boundary anyways for our geometry, let's go ahead and define this region and also use that to define the boundary for where all the calculations will occur, right? So to define this region, I'm going to go ahead and I'm going to use our curve, go to our primitive to draw a shape, and I will just say, okay, draw a rectangle, right? And so I'm going to use, in this case, a rectangle with 2 points, right? So it generates the rectangle using point A and point B. You can define those manually if you like, but I'm just going to leave it at the default and then use that as my region to generate my point cloud. And then also use that as my boundary for the Voronoi calculation, right? From there, we need to input the points, right? So in this case, this probably will make more sense. We have our points. And you see, just like that, we've already kind of generated that diagram, that Voronoi diagram that, we were looking at previously in the example of the Beijing water cube, right? And then, of course, you have some things to modify as well, like the cell radiuses and stuff like that. Now, with the cell radius, let's see if, this is probably doesn't need 100. With the cell radius, what that allows you to do is kind of change the boundary, right? So you can reduce the boundary and then look at what. So really, that's too big. We just need something like a 0 to 1, I guess. So you can imagine if these are all bubbles, right? So the radius function allows us to look at it in that way, right? And then as it expands and they start to bump into each other, right? They start becoming divided, right? And you can see that now, if you look at it, you can imagine they all started with circles, but then, as they arrived at this kind of midpoint between the two, right? They kind of flattened out and became an edge, right? So that just allows you to have a little bit of control over, that characteristic, right? Now, at Zaha's office, what we did with this diagram frequently is that, we didn't particularly like the faceted characteristic of it. So when we were exploring, our landscape projects and stuff like that, we would often rebuild this geometry, right? So we would take this as a diagram, a space planning diagram, and then use our discontinuity component under curves to find those corner points, right? And from there, use our NURBS curve, right, to redraw that shape, right? Now, because we wanted to close it, instead of being an open shape, we would have this periodic set to true. Oops. True. And you can see now, instead of having a kind of faceted diagram, what we would have is a kind of round, more organic looking diagram, right? If we change the degree, it's the same as changing the NURBS curve degree, if you guys remember from our Rhino class, right? So, the higher the degree, the more kind of a fidelity you have in your curve, right? And I think the default is usually 3, but if you want, you can play around, right, and see the effect that has, right? And if we now kind of remove some of that previous stuff, we have this kind of very organic kind of division or cellular division of space, right? So that's another way that you can express, right, the Voronoi diagram instead of just using the default kind of frame, right? But again, all of these things I would, recommend that you steer away from, because unless you have a good reason for using them, as an effect itself, it's a little bit overused and not particularly exciting just because we've seen it so much, right? But of course, this is just a curve diagram, and then, we typically want to be able to look at it, as a surface or a solid or some kind of three-dimensional object, right? Not just some lines in space. And so, one strategy would be to start to build surfaces from that, right? And kind of an easy way to kind of do that would simply be to kind of build a surface using the inside curve and our cells, right? So if we look at the the output from our original diagram, you can see that what we have is a polyline curve, right? 99 of them. And then we have also 99 periodic curves, although these ones, because, you know, of our points here are on a different level. So if we flatten that out, oh, that didn't work. We have to flatten it here. Flatten that out so that the list structure is the same. We'll probably have better luck with our loft. So let's try that now. We say, but need to think about this a little bit. I want to loft cells to this curve. I wonder how that result will be. Because I actually need to put each one. So maybe I need this structure here. And then I want this one to come out as well. So let's use this. No, let's do a graft, right? To change the hierarchy so that these two lists look more the same. Then I go to this one and then this one. And you can see that now I've started to build two kind of surfaces. It's not really ideal though, because, you know, I have a curve and then I have something that's faceted, which is like a composite of several surfaces. So maybe the better way to do that would be to have two curves and use different degrees as a way to create that variation. So now if I do it like this, I get a slightly better result, I think. Uh-oh. I'm asking it for too much. Just wait a second to see if it recovers. If not, again. Okay, so I'm going to, while we're at this stage, reduce the count number so that we have an easier time. We don't have to wait so long after each modification. So let's say 10. Okay. But then our radius now 2. Yeah, I'll just delete the radius. Okay, so let's take this down, take this down. Okay, I won't try to build it then from the original. Let's do something else. Let's try scaling it first, so we'll be able to work with curves that have the same degree in both cases. So use my transform, do a scale function from this curve. The center should be the center of our cells. And we don't have any centers yet. So let's find the center. Now let's go to our curve, look at our analysis tools, say polygon center, right? And then use the cell here, and you can see it found some centers. I'm going to use the center of area for scaling. And we're getting a big mess here because, again, we have something that's on a different, this is a different list structure than this one, right? So I'm going to flatten. I'm going to graft this one. Actually, if I graft here, this will be more clear for you guys. So graft there, right? So you can see now they're both using the same, line type, which means that they're using the structure is the same, right? And so now I have an inner and outer curve, right? And in this case, then I probably, would like it to be, closer to the edge, and then a scaling factor, right? I think we'll just stick with the base slider. And that allows me to control how far that scaling goes. And now if I wanted to do the loft, you can see that I'm lofting from essentially the same geometry, right? Instead of having one being a different degree, they're exactly the same. They've just been scaled down so that now the loft should be more predictable because the curve types are the same, right? So there we have it, right? So we've created kind of a surface in between those two. If we wanted it to have, a slightly different, or just didn't want it to be so flat, we wanted to have a little bit of 3D characteristic, right? What could we do? Well, we could say, take that geometry here, go to transform and move it. Move it in what direction? Let's say we're going to define a unit Z, right? And the factor is a default at 10. Let's ignore that for now. I'm going to go ahead and disconnect the scale geometry from here and then take it from here, right? And so, yeah, so now I have some volcanoes for you guys. Okay, so from there, right, if we go back to our diagram, we can say, okay, now let's change this to some higher value, let's say 50, and have a look at it. So you can see that pretty easy to modify. I want to change this factor to 10, but be able to control it. And the only thing is that, because we started with this kind of populate 2D, right? You'll find that it's a little bit boring also because it kind of evenly distributed those points. If those points had, alternating densities, more dense in some areas, less dense in other areas, you probably would get a more interesting subdivision, right, for this geometry. And what else? So let's try to make this, so let's try to do something to add a little bit more variation to this solution, right? So what might we do? Well, before, in last week's lecture, we were talking about influences and stuff like that. So we had used, distance as a way to create variation, right, in the pattern. And, predominantly we had used like a 1 point or a multiple point. And we talked about how you could use the conditional statements. Sorry, blanked for a second. Conditional statements to, deal with multiple points, right? Now, in this example, let's go one step further, and instead of using points, right, let's say we want to reference a curve, right? So I'm just going to draw a curve that we're going to reference into our definition, right? And let's say our curve looks like this, right? So it's this kind of S shape. Now the evaluation, right, that we're going to do is to see, well, depending on the position of that point to this curve, right, there might have a, it might change the scaling or the whatever, right? So this should make for a more interesting solution than the base case that we're looking at now, right? So, unlike when we were working with single point or multiple points, right, we don't have any really good way to measure, right, our distances from a point, right? So, if let's say I use these center A's, right, to represent the center of that geometry, it looks weird now because, our geometry is three-dimensional and we have perspective involved, right? Those are at the center. But what are we measuring that to, right? There's no point to make a comparison, right? If we were going to do like that distance measurement that we were using before, right? We're typically measuring the distance from one point to another point, right? So what if we're working with a line, we no longer have those points, right? What we need to do is we need to find points on that line, right, to serve as our kind of evaluation point. So if I were to say, I want to measure the distance from this point here, right, to this line, right? How do you think we would do that, right? Because on a line, isn't a line simply an infinite set of points, right? Which point on this line do we want to measure it to, right? You remember that previously when we were working, we were looking at the curve and analysis tools, right? And we found that, there are tools here that allow us to, define points on a curve, like the endpoints or the curve middle, right? Or if we used, what is that one? We were using a point on curve, right? We could define a specific location, right, on our curve. Where's our curve now? Oh, I haven't brought it in yet. So, okay, first, before we get there, let me just remember to bring our curve, set one curve. Okay. Yep. So, we had things that would allow us to position a certain point on that curve, right, to maybe serve as a reference. But, what we want, or I think the most logical way to approach that is to say, well, how do we pick the point that's most relevant, right? And in this case, I would say, if I want to measure the distance from this point to this line, I would measure the closest point on this line to this one, to this point out here, right? It wouldn't make sense for me to measure, this distance from this point to the end of the curve, right? I think it's a kind of logic problem there if you're deciding to do that, right? So what we're looking for then is a way to find the closest point on this line to these existing points, right? And if we go back to our curve and analysis, what you'll find is that there's already a component that does that for us, right? It's called curve closest point, right? So let's grab that one. You can see here that basically what it's going to do is that it's going to take the points that we have, right? So let's say these points, the center points, right? And our curve, and you can see it generated a whole bunch of points on this curve, right? What are those points? Well, those are points that are indicating to us, right, the closest pair, right, that you have to all of these points out here. So we can be pretty confident that the number of points on this list, right, 50, is the same as the number of points that we have, right, 50, in our diagram, right? So that means now it's already found all those lines to compare from. If we wanted, what we could do is we could visualize that, and we could say draw a line, right? An endpoint here and a starting point from the point itself. And you can see that, okay, so the closest point on this curve from here is this one. This one is paired with that one. This one is paired with this one. This one is paired with this one. This one is paired with this one, etc., right? So kindly, they have included something called a distance measurement, right? Which will provide us 50 distances, the distances of all of those relationships. So we don't have to use our distance component in order to find that individually, right? And so let's say, so what can we do? Well, maybe we stick with this scaling, since we already have scaling in our definition here, right? And we say, okay, so why don't we change the scaling factor, right? Depending on the distance, right? That is between the point and that line, right? So you can see, again, we get something weird, right? And that's probably because it's out of range, right? Because the values in our distance are much greater, right, than what we need. So as usual, we have two options, right? We can either use a mathematical function, right? Go to our math and say, divide that value, right, to try to adjust it. Or we can define a domain that we're comfortable with, right? So if we construct a domain, we remap, and we have evaluation of the minimum and maximum, right? So we look first to find the minimum and maximum, right? That becomes our source. The domain that we want is our target, and the value that we're looking at is this distance, right? So by default, this is 0 and this is 1. Let's put that into our factors, and you can see the result that we get looks like this. That may not be clear in that view. Domain. Let me just check quickly what we're getting out of here to be sure. And what we're getting is the same, all of them. So maybe, let me see what happens if I flatten this. There we go. And flatten this one. And then I don't do this. There. Why is this still red? Cannot scale with a factor of 0. So some of them have a 0 factor. So I am going to modify that 0 so that it can at least be something larger than that. So there's a minimum of 0.25. Uh-oh. me reduce this again to look at that more clearly, see what's happening. Oh, okay. So it looks like our loft is, because we broke while we were adjusting this, we also changed the structure of our curves here, right? So they don't have any hierarchy left because we flattened it, right? So let's try to use our graphed component here. Put this here and graphed here as well. There. And now if we increase our count to, say, let's go all the way. There we go. So let me, what is this? Degree must be less than the number of control points. So in some cases we must have, well, that's not a big deal. So you can see here now that in our diagram we have a lot more variation than we did before, right? Because we now are scaling in response to the distance from that line, right? And that scaling applies to the inner circle or the inner cell versus the outer cell. So you can see that, as those points get closer to this line, right, they become more and more closed rather than these ones out here, which are really open, right? If we wanted, I think we can also use this value as our motion, right? So you remember we created a three-dimensional effect by moving them upwards, right? But we did that uniformly across all of those values. So if we were to substitute this factor with our mapped value, right, you see that, well, now actually we are able to vary two things simultaneously according to this line, right? We're varying the size of the opening, right? And we're also creating variation in, the height, right, of our geometry, right? So the closer that we get, the lower, right, those volcanoes become, right? So you can imagine this is a very easy way to, kind of organize stuff along circulation paths if you want, right? Okay, so let's quickly just bake this out so we can have a look at it. I want to group it, yes. Move it to the side, change our preview mode. So you can see that, yeah, we can create, these kind of Voronoi effects and cellular stuff pretty easily. And again, I think it's, it's good for you guys to try this as an exercise as well, because I think a lot of what we covered here, like, working with data structure and hierarchy, right? Evaluating for, points and relationships to understanding how, we can, derive one type of geometry from another, for instance, points from a curve, right? Reviewing this idea of mapping, right? To control the range of values that you're working with, right? So that you're in control of these values instead of accepting just the default. All of these are, I think, very useful practice exercises, right? In terms of getting you guys a good, foundation and understanding of, how to, manipulate data and how to work and what tools are available to you, right? Okay, so that's the end of our Voronoi exercise and probably the last exercise for the day. Try that, give it a shot, and, be aware while you're working on these that, this is just one example, right? So far, we've talked about, several of these, but, probably by the end of the class, no matter what we do, we're only going to be able to utilize about, I would say, 20% of all of these components, right? Of course, the point of the class is not to learn every single component one at a time, but I think to get you guys comfortable enough so that, you know, you guys are able to go in and you know, pick any component you want, right? And start to think about, you know, well, what might that do, right? So for instance, you know, now that we already saw that on the curve tab, we had an analysis for, sorry, on the surface tab, we had an analysis for distance of point from curve, right? Curve closest point, right? You know, when you see under your surface tab analysis, one called rep closest point, you know, you can start to imagine, or surface closest point, you can start to imagine, right, how those work, because they all work kind of the same way. Instead of evaluating the distance from a point to a line, now we're evaluating a distance from a you know, a point from a surface, for instance, right? So, you know, when you learn kind of one thing, you're learning them all across the board. And I think you just need to spend a little more time on your own exploring the interface and looking at the different components that are available to you, because they'll really open up more doors in terms of, you know, what the design tools that are available to you, right? Okay, so that's it for the day.